Hello everyone, my name is Minko. Today I will be talking about math science with the Angular compiler. So here are a couple of words about me. I was part of the Angular mobile team and the Angular style guides team together with John Papa and Igor Minar, Wardbill, and a couple of other folks. And that's actually one of my motivations for building Codelyzer, which is another tool that I'm maintaining. I've been also working on Angular Seed and a couple of other projects that we're going to cover along the way. So I've also written books. I had the privilege there to work with Minko Gechev. So if you're just getting started with Angular, they might be a good starting point for you. And that's, as you saw, I'm quite active on GitHub. That's my GitHub contribution timeline. So a couple of days ago, I was on another conference on the Bahamas. I was super hungry there. So we were on the ship. I went to the last floor. I saw the exact same contribution streak right there. But that wasn't the weird thing. I went to my room, to the bathroom. I saw it there as well. And on a speaker strip that the organizers did for us, we went to Jerusalem. The same thing here. I don't know if it's just me or... All right, so in this talk today, we're going to cover a couple of tools that I built on top of the Angular compiler over the last couple of months. And in order to get better understanding of these tools, how they work, and how we can use them, we're first going to cover how the Angular compiler works and what it does. So in general, the Angular compiler was developed in order to just transform our application into some more efficient version of itself in terms of bundle size or runtime performance, or in this case, both. So in general, the compiler, it is just going to take each of our components and it is going to transform them into something else, which in this case is going to just instantiate the controller of the component, this internal class. It is also going to render the component into the most efficient manner, provide very efficient change detection, and so on. So in general, the compiler is going to generate very efficient views and very efficient provider instantiation. So the individual providers, they're going to be just passed to the controller, to the constructor of the controller of the component. In one word, we can recap that the compiler does transformation. But is that everything that we can do with it? Actually, no, because otherwise my talk was going to be completely pointless, right? We can also analyze the intermediate representation of the source code that the Angular compiler provides, and we can even map this visual representation into the two-dimensional space or three-dimensional space and visualize it. So we can just visualize the intermediate representation of the source code of our application. So we are going to cover these two things, and of course we can do much more, but we're going to focus on the first 2 points only today. But first of all, how a compiler works in general. Because the same way that the Angular compiler works, on lower level it's quite similar to the way that the TypeScript compiler works or any other compilers. Usually the source code goes through similar phases. Just a compiler, we can think of it as a black box which accepts some input and produces an output. In the case of TypeScript, this input is going to be TypeScript source code, and we're also going to have TypeScript configuration, for instance tsconfig.json. After the compilation phase, we're going to get a bunch of JavaScript. If we magnify a little bit, we're going to see that the compiler has a front end and a back end. The front end is usually responsible for just creating an intermediate representation of our source code, parsing it, and after that passing it to the back end, which is going to transform it somehow and generate source code. We're going to be mostly focused onto the front ends today, which has two main modules usually. It has a module for lexical analysis and a module for syntax analysis. The module for lexical analysis, it can be implemented by a function called tokenize, which just accepts as an argument our program, which is just a string, and it produces a list of objects. Each object has a lexeme, which is just substring of the original program, and it also has a type. The type is just what type this token is. It can be keyword, identifier, literal, or whatever. This can be also a stream, of course. After that, we are passing the output out of the module for lexical analysis to the module for syntax analysis. And the module for syntax analysis, it is going to produce just a tree. This is called an abstract syntax tree or an AST. It turns out that these trees, they're extremely convenient for static code analysis. So these trees, we can just walk them around and prove some properties of our program. And the static code analysis is just a form of analysis that allows us to do this analysis without actually executing the program itself. So with the dynamic analysis, we can prove properties of our program as well. However, we need to run the program. This means that the static analysis could be a little bit more restrictive, but it allows us to consume much less resources. And the static analysis is something that I use in Codelyzer. How many of you have used tslint or eslint? Yeah, and Codelyzer? Someone? Okay, a couple of you. Actually, if you have used the Angular CLI, probably you have used already Codelyzer. But in general, Codelyzer is a tool which, similar to tslint or eslint, aims just to provide that our program follows some specific style guidelines. And internally, Codelyzer uses TSC, the TypeScript compiler, in order to go through the phases of syntax analysis and lexical analysis, and uses tslint in order to just allow us to do error reporting, because tslint has very huge ecosystem right now. There are plugins for tslint for almost any popular ID or text editor. So Codelyzer uses it in order to report warnings. Let's see how with Codelyzer we can implement one of the styles from the style guide, that each component should be used with selector of type element. So here we have our tooltip component, which obviously doesn't follow the style. We have selector, which is of type attribute. And well, the first thing to do in order to analyze that our component, to prove that our component doesn't follow this practice, is just to invoke the module for lexical analysis of TypeScript. So now we're getting our list of tokens, and after we get our list of tokens, we need to pass this list of tokens to the module for syntax analysis, which is just going to build this abstract syntax tree. In real life, it looks quite similar to this one, but this version on the slide is slightly simplified. Now, the only thing left is to traverse this tree by using any of the three traversal algorithms that we're familiar with, and find out that the tooltip, the selector of the tooltip, is not actually of type element, but instead it is of type attribute. And we can do this with the visitor design pattern. It is just a standard design pattern initially introduced by the book of Gang of 4, which is very convenient for this case. First, we need to visit the root node, which is just a class, and go through each individual decorator of this node. After we visit the decorators, we're going to find out that one of these decorators is actually called component. We're going to extract the metadata out of the object literal path to the component. We're going to parse the selector, and in the end, we're going to report a warning in case it is not of the appropriate type. So here is how this looks visually. First, we're going to visit the root node, which is the class node. Right after that, we're going to visit each individual decorator, or in this case, only a single one, because there is only a single decorator in our snippet. We're going to extract the metadata out of the object literal, and just report a warning by using tslint that the tooltip selector is not of the appropriate type. So this is already quite powerful, but it doesn't differ much from what we can do with the tools like tslint or eslint. Angular is built with tooling in mind, so it allows us to perform similar type static code analysis on top of our templates and styles as well. Now, let's suppose that we have this header component. And you can see that instead of its styles, we are declaring a style which is actually not used inside of the template, because we have misspelled the span element. Instead of span, we have called it spam. Well, the usual way of verifying that given style have not been applied to the DOM is just by running the program and verifying that dynamically, right? We can just execute everything and see that, in this case, the span label is not red. However, this doesn't scale very well. If we have hundreds of styles, we will not be able to prove that, right? We can miss some we can still miss some styles. The bundle size of our application can grow this way with that CSS. Well, what we can do instead is just to perform similar type of static code analysis by building ASTs for both the templates and the styles, match them against each other, and find all the dead CSS as part of our build process. Here is how this works in Codelyzer. We can find out that the header element here is not used. the header class here is not used. We can find out the same for the div medium. And we can just drop these styles automatically. So this is already quite powerful. It doesn't work always. However, because sometimes we can add these classes dynamically by using the renderer or just by manually manipulating the DOM. However, if we are following some conventions and we are using the declarative approach provided by the Angular's template bindings, we can be quite flexible and we can drop huge amounts of dead CSS from our application. Now let's talk about something not that fun, I guess, something quite painful. This is breaking changes. I guess how many of you were quite scared between the breaking changes from AngularJS to Angular? Yeah, don't be shy. I know that. I went through the same phase as well. So with the Angular compiler, we can do something about that. The Angular core team, they're doing an amazing job right now making sure that we have the least amount of breaking changes possible between Angular versions. And they did an amazing job allowing us to have the smoothest transition process between Angular 2 and Angular 4 possible. However, there are still a couple of deprecations. For instance, the template element is no longer called template. It is now ngTemplate. We have renderer, which is renderer 2, and so on. Now let's see what is going to be the most convenient way just to transform our Angular 2 project to Angular 4 and rename the template element to ngTemplate. We can think about this as a string replace, like search and replace, right? However, there are some corner cases when this simple string replace thing is not going to work. For instance, let's consider this case. We have template element inside of the template of the component. However, we're also mentioning it inside of the string literal, which is the value of the content property. In order to handle this case, we can still build this intermediate representation of our application, and we can provide some context-aware replacement. So this is a tool that I prototyped a couple of weeks ago called ngmigrate. So ngmigrate is currently an NPM module which allows us to just plug different migration strategies which are going to migrate specific part of our application. It is just a global executable file which accepts a pattern, a glob with all the different files that we want to analyze. And but before running the script, let's take a look at the source code file. So this is exactly the same case. We have our template element inside of the template of our component, and we are also mentioning it inside of the string literal content. After we run ngmigrate on top of all of our TypeScript files, the tool is going to find out that we have a couple of deprecations inside of the about.component.html template and a few other templates as well. If we agree with the tool that we allow the tool that to perform these migrations automatically for us, it is going to perform them, and we can just see what it does, what it did. So all the migrations were applied successfully, and this string here was left unchanged. This can be applied for different types of breaking changes, not only inside of our templates, but also within our styles as well. And this can make the migration possible between versions very simple. Alex Eagle from the Angular core team, he's working on extending tools similar to ngmigrate in order to provide us very smooth migration process. Now, let's talk about source code visualization. Now, let's imagine that we're new to a huge project, and we need to get into the system as soon as possible in order to become productive. So we have hundreds of components, hundreds of thousands of lines of code that we need to read in order to start contributing to the project ourselves. And usually having that much source code, it is very hard to digest. And also, usually the different components and different modules, they're going to be on different level of abstraction, which is going to be even harder for us. In order to apply the in order to get used to the project, we need to apply some systematic approach of exploring it, for instance, top-down or bottom-up, where we will be able to just get used to the system as quickly as possible. And also, we are very good in visual thinking. So that's why there are so many tools for reverse engineering of Java or C# applications. That's what I thought, why I thought, well, let's build something like this for Angular. And I started using the Angular compiler for this purpose. However, it provides very primitive API because it was built for. That's why I built a wrapper on top of it called ngast. And well, ngast is a wrapper, as I mentioned, which provides higher level API that allows us to just analyze, get all the different directives and components out of our application, get their metadata, see what is the relation between the different providers, see their dependency, see the dependencies of the providers and the components and so on. And on top of this, I built a tool called ngrev, which is a module for just an Electron application for reverse engineering of Angular apps. Here's how it works. It is just an app that we can start from our toolbar. We can select a test-config file from our project, and the application is going to render the root module of our application and all of its dependencies. We can explore the dependencies one by one, or we can just select the app module and explore its providers or bootstrap components. If we select user service, we'll see all the different dependencies of the user service itself. We can click on them to see their metadata. We can go back and explore the actual app component. We can see that the app component has a single dependency. It also has a template where we have the header, the layout header, and the layout footer. If we double-click on the layout footer, we're going to be redirected to the actual component which implements this functionality. And for the different elements inside of our templates, we can see all the different directives which are attached to them. After we go back, if we want to explore any of the components even further in depth, we can just open it into our favorite text editor IDE. That's it. It's already... Yeah, thank you. So this is already useful. I've used it for personal projects. I've also seen it being used in some big companies. However, well, it's fun, but it can get even more fun. So we can go one dimension higher, one dimension above. This was mapping of our source code into the two-dimensional space, but we can even do that in the three-dimensional space as well. So we can create reality for our source code if we like our source code that much that we want to live in it, and just render it out of our source code this way. How many of you have actually seen the ngworld demo from ngconf? Okay, only a few of you, so this can be interesting. I did some improvements on top of it. So this is another demo that I built for just for fun. This is called ngworld, which is another NPM module that you can install by using npm, and it accepts as an input just an Angular project. So I'm going to open the Angular seed. Before that, let's just take a look at the Angular seed itself very quickly. So Angular seed has a shared module here, which shared module is being included into the app module. And the shared module has a couple of declarations. It has a toolbar component and a navbar component. If we go into the toolbar component, we're going to see its template here, which template has only an h1 element and a div. Right, so that's one module that we're going to visualize somehow. After we run ngmigrate, oops, not ngmigrate, but ngworld, ngworld is going to perform the same phases that we described for compiler. So it is going to go through lexical analysis. After that, syntax analysis. It is going to transform the ASTs that it has built, and in the end, it is going to do some code generation, source code generation. So this is the source code that has been generated. We are going to open this in our favorite browser, and we will see that we are in a virtual reality here. There is sky and grass. There are some gardens. If we go closer to the gardens, we're going to find out that this is actually our shared module. And inside of the shared module, we have a toolbar component, which has the exact same template, like exact same crown. Yeah, so we can jump around. And well, you know about the term introduced by Webpack called tree shaking, right? So I guess we can tree shake these trees. But before that, let's open the toolbar component. Because tree shaking, it is usually related to dead code elimination. Well, in our case, we're not going to eliminate dead code. We are actually going to eliminate code out of the template itself. Yeah, we can do the same here. We can just start shaking trees. So my point with this presentation was not only to show you that we can build some useful things with the Angular compiler, because obviously we can. We can build just, we can transform our application to some more efficient version of itself, or we can visualize the source code of our app. We can even build a crazy virtual reality out of it. The purpose was also to see how much flexibility the Angular compiler provides to us, and that the only limit that we currently have is our own imagination. And thank you very much for your attention.